Welcome everyone to another OCP Tap call. This is call number 155. It's my pleasure to introduce Ankur Sharma. Ankur is a technologist at Equinix, where he works on distributed infrastructure, multi-cloud networking, AI systems, and time synchronization at scale. He's the architect behind Equinix Precision Time, the industry's first time as a service offering, and he has led several initiatives across AI infrastructure and observability platforms. He's also actively engaged with the broader ecosystem, contributing to efforts within OCP, including the Time Appliances Project, as well as WSTS and Agentic AI Foundation, with a focus on timing, observability, and distributed AI systems. Today Ankur will share insights into how causality can break in observability systems for distributed AI, even when the underlying systems remain correct, and what this means for the future infrastructure design. Please join me in welcoming Ankur.
Hi everyone, and thank you for joining. I'm Ankur Sharma. Like Ahmed mentioned, I work currently at Equinix, mostly on distributed systems, timing, and infrastructure. Lately, I've been spending a lot of time chasing down weird, behavior of AI pipelines, and that's how I ended up going down this rabbit hole of time, causality, and observability. At first glance, this sounds like a timing talk, and it is, but it is also a distributed systems talk, and observability talk, and increasingly an AI infrastructure talk. The central question here is actually very simple. What happens when time is slightly wrong in a distributed AI pipeline? Most people would instinctively think that if time is a little off, maybe some timestamps are noisy, maybe some graphs get a bit messy, but if the system still works, we are probably okay. So what we found is that this assumption is dangerous. A distributed AI system can continue functioning correctly. It can keep producing outputs. Throughput can stay stable, performance can look normal, and yet the observability layer, meaning the way we understand the system through traces, metrics, and causal relationships, can already be broken. So the big message I want to land today is that the system can still work while your understanding of the system is already wrong. So that is the problem this talk is all about. Before I get into the technical content, I want to quickly acknowledge the context of this talk. This is an OCP Time Appliance Project Industry Community session, and it sits within broader Unified Intelligent Infrastructure workstream that we have initiated at under OCP Time Appliance Project workstream. That is very fitting place for this discussion because this problem does not belong to only one community. Uh, like timing experts have been thinking for years about synchronization, precision, stability, traceability, and the consequences of clock drifting apart. Distributed systems people have been thinking about ordering, consistency, observability, and failure analysis. Similarly, AI infrastructure people are now thinking about how to operate increasingly distributed inference and agentic systems at scale. So this work sits right at the intersection of these all these domains. So part of what I hope this talk does is not just share one set of experiments, but also help connect conversations that have often happened separately. Timing is no longer just a background infrastructure concern. In distributed AI systems, timing becomes part of the trust model of the system itself. Let's start with the motivation. Distributed AI systems rely on precise timing for coordination, ordering, and observability. That part is easy to say, but I think it is still underappreciated in practice. When people look at distributed AI system, the focus is often on model quality, latency, throughput, infrastructure utilization, GPU efficiency, and transport performance. Those things matter a lot. But underneath all of that is a quite assumption, and that assumption is that time is good enough. The problem is that even milliseconds of skew can silently corrupt your understanding of system behavior. And that is a phrase I want to emphasize here, your understanding of system behavior. I'm not yet talking about the system immediately crashing or producing bad answers. I'm talking about the traces, the timing relationships, the ordering, and the operator's mental model of what happened. And this is where the observability trap comes in. We trust our dashboards, we trust our traces, we trust our metrics by default. But what if the data itself becomes causally incorrect while the system still appears to function perfectly? That is really the core question that motivated this work. So the question is like, can observability fail before system functionality fails? And if so, how much skew does it take to fail it? This slide is where we define the challenge clearly. The problem is that distributed AI inference systems can remain functionally correct and performant, yet their observability may break because of the clock skew between the nodes. That distinction is very important. The system works, inferencing continues, throughput is stable, responses are correct. But if you are looking for from a purely functional perspective, everything appears normal. At the same time, observability can break, traces can show negative spans, ordering violations can appear, causality can be violated, and your window into the system becomes unreliable. This is what I call silent failure. You may not notice it immediately. You may only notice it later when you try to debug an issue or understand a latency spike or reconstruct the sequence of events across the pipeline. By then, the problem is already operationally expensive because the system that is supposed to explain what happened is no longer trustworthy. And that is why I wanted to explicitly define causal correctness here. If event A causes event B, then A must appear to happen before happen before B in all observation. When clocks are skewed, that basing relationship can be violated. And once that happens, the root cause analysis becomes much harder because the observability layer has stopped preserving the reality. So before we get into the pipeline and the results, I want to level set on a few key concepts throughout this presentation. Firstly, distributed pipelines. AI inference workloads often flow through multiple processing stages across different physical nodes. A request is generated, normalized, sent for inference, and then post-processed before it is complete. That means the full path of one request spans multiple systems, not just one process or one host. Secondly, the timestamps and ordering. Each event is timestamped by its local clock. That means correct ordering across the distributed system depends on synchronized clocks across all nodes. If one node is ahead of another, then events on the second node may appear to happen before the things that actually cause them. Thirdly, observability systems. Metrics, logs, traces are the tools we use to understand distributed systems, but all of them, especially traces, really rely on timestamps and being meaningful enough to preserve causal structure. And last and the fourth thing is the negative spans. A negative span is where the child appears to start before the parent. That is physically impossible in causal correct systems. So the negative span is one of the clearest signals that clock skew is distorting the trace. So this slide is really the conceptual foundation of the whole talk. Once you accept that distributed observability depends on local clocks, it becomes much easier to understand why a little skew can have such a large impact. This is the actual pipeline architecture we use. The flow is straightforward by design. We have a producer that generates inference requests and assign initial timestamps. We have a preprocessor that tokenizes, normalizes, and prepares the input data. Then we have an inference stage that runs the model and generates the tokens. And then we have a post-processor that formats output and logs completion timestamps. So there are three key things to notice on this slide. First, each stage runs on a separate physical node. That means each stage has its own independent system clock. This is not just multiple functions inside one machine. It is a genuinely distributed setup. So on the second thing is like the inference node is the skew target. That is the stage where we introduce controlled clock skew. And I want to emphasize controlled clock skew. We'll see that throughout the slides. We do that deliberately so that the experiment remains clean and easy to interpret. Third thing, the components communicate through a message transport layer, and timestamps are propagated end to end. That allows the downstream stage, especially the post processor, to compare upstream timing with downstream observations and detect where causality begins to break. So this architecture is simple enough to reason about clearly, but realistic enough to expose real distributed timing behavior. Now, let me explain how we tested this. The environment includes the pipeline nodes, orchestration and monitoring, and a time synchronization source. The structure of the experiment is intentionally controlled. First, we establish a baseline with NTP synchronized clocks across all nodes. Second, we introduce a controlled clock skew at the inference node only. Thirdly, we measure system behavior and observability metrics at the same time. And fourth, we gradually increase skew magnitude to identify where failures first begin to show up. The metrics we collect are token throughput, negative spans, ordering violations, and causality health. I want to emphasize something here. This is not a vague, we saw some weird traces type of experiment. This is a controlled intervention. We keep the system stable, we change one timing variable, and we observe what happens. That gives the results much more structure and makes the conclusions much more defensible. We are basically treating skew as the intervention and observability failures as the outcome. Let me spend some time on the transport layers because this is an important part of the how the experiment evolved. So initially we started with Kafka because Kafka was the original transport we used in the pipeline mainly because it was already familiar with like we were all very familiar with that and already used in many environments and gave us a stable way to stand up the distributed workflow quickly. It was a practical starting point, not a theoretical one. We used Kafka to get the first version of the pipeline running end to end and to establish the early timing and observability behavior. From there, we wanted to reduce broker influence and simplify the transport path. So we also moved to zero MQ. Zero MQ gave us a brokerless architecture, a much simpler setup, and faster iteration. That was very helpful because it allows us to isolate the timing behavior more directly without dealing with Kafka broker semantics in the middle. Now, Aeron is under active exploration, but I want to be precise here. We have not yet completed the main experiments on Aeron. We initially ran into some Python binding and integration issues, especially around getting the bindings working cleanly in the current stack. So at this point, Aeron is not being presented as a completed transport result. It is promising path, and we are continuing to work on it. But the results I'm discussing today are based mainly on Kafka and Zero MQ. So the clean way to think about the transport story is this. Kafka was the initial baseline transport. Zero MQ became the practical brokerless transport for rapid experimentation, and Aeron is still under investigation and not yet part of the validation set. So that distinction actually matters because I want to be careful not to overstate the transport validations. And the reason zero MQ became so useful for this phase is that it gave us a very simple transport path, very little operational overhead, and a clean way to focus on actual question, which is not transport performance by itself, but how clock skew affects causal observability in a distributed AI pipeline. Uh, this is a slide about how we measure what is happening. We track token throughput as a primary system performance signal that tells us whether the inference pipeline is still processing tokens at a healthy rate. We track negative spans as a clearest signal of causality violation. If child spans appear to start before parent spans, that is direct evidence that clock skew is corrupting the trace. So we track these ordering violations, which capture events that appear out of sequence relative to their actual dependencies. And we track causality health, which is a composite score from 0 to 1, representing overall trace validity. 1 means healthy, 0 means essentially broken. So the reason this metric is this metric set is powerful is that it separates system function from observability integrity. Uh, Throughput tells us whether the system is still doing work. Uh, then negative spans, ordering violations, and causality health tells us whether the system is still telling the truth about that work. And that separation turns out to be the most important thing in the whole experiment. So let's start with the baseline results. Now at zero skew, the system behaves exactly the way we want. All components are functional, throughput is stable. Throughput is stable around 850 tokens per second. This is just the rate that we have set in the experiment. There are no negative spans, as you can see on the graph, and causality health is at 1.0, like basically at 1. This matters for two reasons. First, it confirms that the pipeline itself is healthy. Second, it gives us a clean reference point for comparison. We now know what correct looks like. This baseline metric visually reinforces that this is the controlled environment. Clocks are synchronized, drift is small, the observability layer and the system behavior agree with each other. So this is a standard against which everything else is measured. With the baseline established, we then begin the skew injection experiments. The design is intentionally simple and controlled. So we inject skew only at the inference node, which is node C, the third node. We do that so we can clearly attribute observability failures to a specific time misalignment rather than to multiple simultaneous variables. The skew range we tested in this phase was from 1 millisecond to 10 milliseconds in controlled increments. Each test we ran, the run long enough to produce meaningful data, and conceptually we divided the progression into three different ranges: 1 to 3 millisecond as the low skew range, 3 to 5 milliseconds as the transition range, and 5 milliseconds and above as the high skew range. The skew injection architecture shown here is very important because it makes the experiment easy to reason about. The producer, preprocessor, and post-processor remain aligned. Only the inference node receives the timing perturbation. Then that actually lets us ask a very clean systems question, like what happens to observability when just one stage in the distributed AI pipeline starts operating on a shifted clock? So the first result is reassuring. In the 1 to 3 millisecond range, the system behaves normally. Token throughput remains stable. All pipeline stages function correctly. We do not see any performance degradation. More importantly, causality remains intact. There are no negative spans. Observability is still trustworthy, and causality remains at 1, and we do not see any ordering violation. So this gives us a clear, safe range. At, at least in this setup, small skew below roughly 3 milliseconds is tolerated well by both application and the observability layer. That is important because it tells us the system is not infinitely fragile. There is a range in which a little skew does not visibly break causality. But that safe region ends sooner than many people might expect. This slide is where the behavior becomes interesting. Around 3 to 4 milliseconds, we begin to see first negative spans. The system still works, but observability starts to degrade. That is the key phrase here. The system still works. We are not yet seeing application failure. We are seeing observability failure first. So this slide also calls this a threshold region or a threshold range. And I think that is the right way to interpret it. This is not a smooth linear decline. Small increases in skew now start producing disproportionately larger effects in observability behavior. Negative spans begin appearing, causality health starts dropping, and the system is entering a new regime. And what I find especially interesting is how small this threshold is. Like a few milliseconds sounds modest in many distributed system environments, but here it is enough to begin corrupting the causal story told by the observability behavior, the observability layer. That is why this threshold region or the range is so important. It tells us that observability can become fragile earlier than many operators might assume. So once we move beyond 5 milliseconds, the pattern becomes very clear. The system still works, throughput remains broadly stable, inference continues producing correct results. And that is the first point to notice because it means the application path is still resilient. But now negative spans surge, causality violations become frequent, and ordering anomalies appear. You know, events begin to look out of sequence in traces. So at this point, the application is still productive, but the observability layer has become unreliable. This is the dangerous state. If you only looked at throughput, you might think the system was healthy. But if you're if you care about debugging, replay, root cause analysis, or understanding latency behavior, the system has already become much harder to reason about. So this slide really captures the core split between operational function and observational truth. This slide is really the center of the entire presentation. Observability can fail before system functionality fails. I think we all saw that. That is the core finding. The system works, throughput is stable, the responses are all correct, performance is intact, but at the same time, clock skew increases, causality degrades, and a gap emerges. Eventually, observability breaks, negative spans appear, traces become unreliable, and you are effectively debug blind. And that is the dangerous state described at the bottom of the slide. You believe your monitoring is working, but it is showing you an incorrect picture of reality. That is worse than complete failure in some ways because it encourages false confidence. A complete failure is all obvious, at this point, and a causally broken observability layer is often not. On this slide, basically this slide makes the divergence visible. The green throughput signal remains stable even as Q increases. So from the system performance perspective, things still look resilient. At the same time, negative spans rise sharply. That is a very strong signal that observability is degrading, and causality health drops from healthy to almost unusable. So what this graph shows is not just failure, it shows misalignment between two views of the system. The system is still functioning. The observability layer is no longer faithfully describing that situation. That gap is the key story. If all the curves were collapsing together, then we would simply be looking at a stressed or a broken system. But here, throughput stays flat while causality health falls off dramatically. That that means application health and observability integrity are diverging, and that is exactly the problem we want to expose. And we'll see that. Yep, basically. So one of the most interesting things we observed was that the failure behavior was not always monotonic. In some longer runs, negative spans would rise rapidly after skew injection and then stabilize, and then causality health would begin to improve again. That was unexpected. You might assume that if you inject a fixed skew, the system should simply remain in the correspondingly degraded state. But what this slide suggests is that even static skew experiments are actually dynamic in practice. The likely explanation is the relative clock drift between the nodes. Even if skew injection itself is static, the actual effective skew between the nodes changes over time because different oscillators drift differently under different conditions. That means the system can move into and out of causally broken state over the course of run. And that is very realistic. Real distributed systems are never perfectly still. Clocks are always drifting, temperatures are changing, loads are changing, and the timing relationship is always evolving. So the self-recovery observation is not just a curiosity. It tells us that the real-world timing problems may be more dynamic and more subtle than simple fixed offset models suggest. So this slide captures an important operational lesson. Before we tightened synchronization discipline, we observed large clock offsets in the environment, in some cases well into the hundreds of milliseconds. That was a major finding. It also showed us before you even begin timing sensitive experiments, you need to validate the infrastructure time baseline. After fixing synchronization, implementing drift monitoring, and verifying offsets more carefully, we were able to establish a reliable baseline. And the message here is bigger than the experiment, that infrastructure time is not something to assume. It must be measured and validated. So hardware matters, oscillator quality matters, network latency, symmetry matters, and environmental factors matter, and temperature and load can also can influence the drift. So one major lesson from this work is, before running time sensitive experiments or before trusting time sensitive observability, verify the time infrastructure first. Otherwise, you risk drawing conclusions from a moving and poorly understood baseline. So on this slide, basically, like there's a like this slide needs a slightly careful framing. So let me be precise. So what we have validated so far is that the causality failure pattern appears across Kafka and ZeroMQ. In both of those transport modes, we see the same core behavior. The system can continue functioning while observability degrades under clock skew. So we see negative spans appear, causality health degrades, and the same general threshold behavior emerges. So at this point, the strong statement we can make is that the issue is not specific to Kafka, and it is not, and it also persists in brokerless zero MQ setup. That is already important because it tells us that the phenomena is not just an artifact of Kafka's broker model, topic behavior, or buffering semantics. When we remove the broker and move to a simpler direct messaging pattern like with zero MQ, we still see the same fundamental causality problem under skew. Now on Aaron, it's this one as we talk, like it is still under exploration. So, like we are working on it and we'll probably have more results on that in the future. Uh, so what are the broader implications of this work? Firstly, distributed AI systems are vulnerable in a way that it is easy to miss. As inference scales across nodes, timing becomes critical not just for performance, but for trustworthy observability. Secondly, observability tools themselves need to become more timing aware. If they do not account for clock skew, they may present operators with a misleading view of the system. Thirdly, debugging and replay become much harder when timestamps are correct. Once events appear out of order, basic questions like what happened first becomes difficult to answer reliably. And the fourth one, multi-agent systems are also implicated because of this. If agents are coordinating across nodes and services, they depend on reliable causal ordering just as much as any traditional distributed system does. So the hidden risk here is that organizations may have AI systems that are operationally fine while their observability is already broken, and they may not discover that until a critical debugging moment. This problem also connects very naturally to broader industry directions. Open telemetry is becoming the common language for observability, and our findings suggest that skew detection and causality validation should become much more visible in those ecosystems. Distributed tracing systems like Jagger and Zipkin, they also need to think carefully about how they represent suspect traces when clocks are misaligned. Timing infrastructure remains foundational, of course. NTP, PDP, PPS, White Rabbit, they're not just low-level timing technologies. They increasingly influence whether the observability story in distributed systems can be trusted or not. And financial systems are a useful comparison point here. Finance has understood for a long time that the precise timing is not optional because causality, reconstruction, regulation, and ordering all depend on it. So what I think is happening now is that distributed AI systems are entering a similar phase where timing is moving from optional hygiene to an operational requirement. So the work is not finished yet. I mean, whatever we are doing, this, basically the slide that tells us what we're planning to do next. First thing, we want to do a finer grained skew sweeps, especially around the threshold boundary to characterize the transition more precisely. Secondly, we want to move beyond single-site experiments and test across data centers and regions where latency and synchronization become more challenging. Thirdly, we want better instrumentation. So we want tooling that can automatically detect and report clock skew from trace behavior itself. Uh, Fourth thing is we want per edge analysis. Right now, we know the system crosses into causality failure, but we want to isolate which edges and relationships are most sensitive. Uh, Also, we want to explore tighter hardware timing solutions, including PDP, PPS, and White Rabbit. We are also interested in correction algorithms that could potentially adjust timestamps or at least identify, suspect spans automatically at runtime. So these experiments are the beginning of the larger research and engineering direction, not the end. So yeah, there is a lot work to be done. Now, at the same time, this is very much a community problem, and that is why I want to make collaboration explicit. We welcome contributions in code, experiment design, analysis tools, and instrumentation. We would love to see reproductions in other lab environments on different hardware with different workloads and with different type of transport mechanisms. We also would love to have feedback. What are we missing? What would your what would you test want to look or test next? What assumptions should we challenge? What failure modes should we add? And more broadly, I think this is good example of a problem that benefits from people with different expertise working together, like timing experts, AI engineers, distributed systems people, networking people, and observability folks. This is exactly the kind of issue where no one discipline has the full, picture by itself. This work is not happening in isolation. It stands on a lot of prior work in clock synchronization, causality tracing, and distributed systems. The OCP TAP community brings together data center operators, developers and vendors around timing technology. And the timing community includes PDP, NTP, White Rabbit, precision synchronization research. The observability communities include OpenTelemetry, Jagger, Zipkin, Prometheus, and all of the broader work on tracing distributed systems. And beneath all of that is the long history of research around causal ordering, vector clocks, Lamport timestamps, and distributed system reasoning. So, what I think is new here is what we are explicitly connecting those bodies of work into modern distributed AI systems. And that is what I mean by connecting these domains for the AI era. Uh, the if I leave you with just one message, it is basically, in summary, what you see is like the system works, throughput stays stable, and responses you're getting from these systems are correct, and performance is all good, intact. But clock skew grows, causality breaks, and that's when the gap emerges. So observability breaks, the negative spans appear, traces become unreliable, and you become effectively blind to what is really happening. So that's where timing really matters. Even small clock skew can silently break your observability while everything else appears normal. And that is the core message of this talk. Like, in distributed AI systems, timing is not just a background infrastructure detail, it is a prerequisite for trustworthy observability. I want to, thank, before I close, I want to acknowledge the people who are really helping to shape this, the thinking around this work, through conversations, feedback, collaboration. Some of the names that you see on the screen, they have been actively involved in giving us the feedback, running these experiments in the lab, helping with the coding, So basically, this topic really benefits from cross-domain discussion, and I'm grateful to all these people listed here and others who help challenge assumptions, offer ideas, and think through the implications. A lot of the value of this work came from combining the timing perspectives, infrastructure perspectives, observability perspectives, and obviously the AI system perspective. So I really want to explicitly thank everyone who helped push the work forward. I think David is on the call, and some of our others like Paul also is there. So yeah, really thankful to all of them helping us right now. So yeah, I mean, that's the last slide. So thank you all for your time and attention. And also, I would be very happy to take any questions, comments, any alternate interpretations or ideas for next experiments. And I would be especially interested in hearing from people who have seen timing related observability issues in their own distributed systems, whether in AI or finance or networking or other infrastructure domains. And I think there's a lot more here for us as a community to explore together. And the QR code that you see on the screen is that will help you take to the workstream homepage where you can see there are a lot of upcoming meetings and the work by we have a bi-weekly meeting where we discuss these experiments, and we are continuously working on it. So any kind of contribution, you can join this work stream and help us, at least like give feedback or either way. Yeah, that's it. I'm open for any questions or any.
So Ankar, amazing presentation. I really, really enjoyed it. I think you guys are doing some amazing work. There were some questions in the chat. I
Oh,
think Paul had put something there. I don't know if you want to go through his first, or I can go through mine, and Sahas
yeah,
also has some
yeah,
questions.
sure. Let me check the chat. Why atomicity matters to AI infrastructure snapshot. Okay, yeah, thanks, Paul, for sharing that. I'll definitely take a look into that link you have shared. Awesome. Yeah, Dan, please go ahead. I see your comments, but
Yeah, so
like,
I thought it was interesting that there were issues between 3 and 4 milliseconds of skew, and
mhm,
I'm just wondering, where do you think that 3 or 4 milliseconds comes from? Is it latency over the network? Is it something embedded into the system itself? So in other words, maybe they already looked at this is a problem, time is a problem, so we are going to purposely limit the operation of the AI system to milliseconds. And if
mhm,
that's the case, could we, if we had better timing, remove those limitations or reduce them to, say, 3 microseconds of skew or,
mhm.
sub-microsecond skew? So my question is, are these limitations just an embedded thing that people put to make things work, or are they true physical limitations? Or do we know?
Yeah, I mean that's a great point. Great question actually, Dan. So it all my I would start with saying like it all varies from system to system and how your environment, your lab is set up. Like these experiments that we have been doing, all of those nodes which we talked about, they are sitting in the same rack in the same data center.
Hmm.
We plan to definitely distribute those nodes across different data centers, but current experiments, and all the time synchronization happening on these nodes, the grandmaster clock is sitting exactly in the same rack. So we are getting the time from GNSS, and then have a grandmaster which distributes the time to all these nodes. We are using like a local NTP, our own local NTP server. So now within the same rack, there is probably the minimum amount of latency between those nodes. So you know in a setup like what we have, and the resources running on those servers and nodes, this is what we are seeing. Like now 3 milliseconds is the cutoff range or the threshold where we start things to go uh, negative. Like we start seeing those negative spans. But in a real world situation, which we plan to do next, like with real GPUs and everything, like a high scale real world scenario, we may not see 3 milliseconds as the threshold. If you have better synchronization, or maybe uh, like it all also depends on when you see that pipeline. There is a producer node which is basically generating the request per second. Now those requests are like how in a real world different users, they trigger prompts as individual isolated requests coming into the inference system. So, it all depends on what is your rate of request coming in and how much or how many tokens per request are getting generated. So, if that mapping is misaligned, so those are the parameters which we are also tuning in our pipeline. So, as long as we have the flexibility to control these things, like what should be my request rate, how many requests or how many clients in parallel, or what is my you know uh, ingestion rate for the request coming in,
Hmm.
versus how many tokens for each request I'm generating. So all of these different factors which we can tune to mitigate the impact of how, like your nodes are synchronized, or how we can, that 3 millisecond range, the number can actually move to 10 milliseconds or maybe 50 milliseconds, depending on how well your systems can tune those parameters.
Yeah. I'm just wondering, I remember, I think Meta and I think even AWS and others have presented how they were able to improve their databases by reducing skew to, one or a couple microseconds. So I'm wondering if you could get much more higher token performance
Mhm.
with more accurate clocks. And so that
Yeah,
was
absolutely. Yes. I mean, we have the lab that we are using right now to run these experiments have limited resources currently, and David, who is on the call, is also helping us set up a better lab in his in his fintech lab. So yeah, that's the kind of help we are looking forward to, because it's always challenging to get the right infrastructure, and we definitely want to run the same pipeline, the same experiments in different kind of labs to see, this 3 milliseconds is maybe a different number in a different lab. So that's where we want to do things next.
awesome. Good work. Thank you.
Thank you. I don't know, like maybe there are more questions. I see Sahas has a question. When you say observability degrades, after a few milliseconds of skew, are there attempts to paint over obvious errors or make it usable, or is there the point where it's just not worth looking at your logs? Uh, I mean, I think my answer would be, I think I pretty much explained in my previous comment also, but 3 millisecond is just what we have seen, it doesn't mean that it doesn't make sense to look at the logs more, but in our system, in our lab, 3 milliseconds is the range when we start to see that, observability has broken, and, basically the tokens which are flowing, they are out of order, and you may probably start seeing, issues with like traces spanning across those nodes. But yeah, like I said, that number could be different in a different lab and environment.
Yeah.
Hope that
Sorry,
answers.
my mic was not working at that moment. But yeah, thank you, Ankur, for your presentation. A very interesting experiment. So yeah, I just kind of wanted to get a picture of like what you defined as the threshold, really. Kind of like why, like, was there some wall or something that you kind of hit, or um, I guess that wasn't too clear to me. Was-
Yeah, no, I mean, in our lab, what we are doing is, there are a few things which we are able to we are tuning right now. Clock skew, definitely, that is the main thing that we are injecting to break the observability. But at the same time, let's say we introduce 3 milliseconds of clock skew, but if we have a different request rate and a different tokens per second generation rate, that 3 milliseconds could be 2 milliseconds or 1 millisecond. How basically that 3 milliseconds is you're giving a time bound or a window for observability to stay normal or stay intact. But if you reduce or if you change the rate of in request or the tokens generated per second for every request, that thing, if you keep on increasing that, depending on how your system, what resources you have, it can break the observability sooner also with just 1 millisecond or 2 milliseconds. So
Okay, yeah.
it is extremely variable. What we are trying to do or give out of this experiment is like, uh, you need to know the time running on your systems really well in order to tune the parameters for your inferencing on those nodes, and how to look at what numbers, what parameters to look into.
So Ankur, I have a question for you.
Yeah.
So, do you use in-band telemetry? Like
Uh,
you collect the data in-band, like the packet itself, which carries whatever information used for training or inference. You collect the information for monitoring and telemetry, which you send
we
to some centralized server for analysis.
Yes, we collect all the telemetry. Currently, we are collecting all the telemetry from the very last node in the system, which is the post processor node. That is where
Mm.
we are basically passing all the information from every node and accumulating everything on the post processor, and that is where we collect all that data and plot and see what is
Yeah,
happening.
but how you collect the data from each node, in band or out of band? Like
Uh,
if I have a node like a server or a GPU or what GPU, for example, you go to every GPU and you collect the data. How you collect it in a separate packet, or you collect how you collect it?
uh, like, I'm not sure if I got the question,
Mm.
Hisham. So you're asking, like, are we collecting the packets on the same interfaces where the data is flowing? Is that the question, or?
Yes, exactly. Yes, yes.
Okay. Uh, there is only right now on our system, the nodes that we have, we only have one active interface. So pretty much all the data collection, telemetry collection, and data flow is happening on the same interface. One thing which I want to highlight is we are, like, in the very beginning of the presentation, I said, like, it's a very controlled environment with respect to how we correct the clocks and inject the skew. What it means is we do not have a live running P2P synchronization or NTP synchronization. We just
Mm.
synchronize all the nodes in the very beginning of the experiment, and then we let the clocks drift like naturally. And but yeah, so there is no time packets running on those interfaces, but all the data and telemetry, everything is happening on the same interface. But again, like, we are not collecting telemetry or, from every node. So that's why we collect the telemetry at the end, because we don't want
Mm.
to impact the actual traffic flowing between those nodes, the
Yeah.
tokens and
And,
everything.
and at the end, how you collect the telemetry? You collect it from the interface?
Yes, so we have, yeah, we collect it from the interface. Correct. That is right.
Yeah. So you just read the interface information and maybe you send it to some
We
place to
have
analyze it.
Exactly. We have a fifth node in the system where we have Prometheus, Grafana, and the observability tools running. So we
Yeah.
plot everything there.
Got it. But so is you don't use in-band telemetry.
Yes, yes, that's right.
Yeah. By the way, I wrote a paper last few days about a new algorithm for telemetry and observability
Okay, awesome.
and how it
Yeah,
relates to time synchronization. I will do some little bit of editing, Anchor, and I
yeah,
want to send it to you. Please read it and let me know how you think of that algorithm.
perfect. I would be happy to take a
The
look.
paper, I was thinking really to send it to a conference like SecCom, but it cannot be accepted. You know why? It's all theoretical. We need
Mhm.
what you are doing, which is pragmatic and empirical evaluation. It is
Right.
really the big value of what you are doing, really. You have a
Yeah,
lab, you measure things, it is excellent. So just read it, Anchor. See
sure,
if
sure.
this algorithm can be useful, can and if the paper is in good shape, we can submit it. If it is at the end, because SECOM is very, very critical. It's not easy to get paper accepted. But if you have
I
good empirical analysis and the theoretical foundation is fine, we have a chance. If not, we don't have a chance.
Absolutely. Yeah, I totally agree with you. And also, the one good thing we have in this experimental lab is, like, all these algorithms that Hisham you mentioned, we can tune the applications to use any custom algorithm. So
Yes,
this
exactly,
this
exactly. And I think one of the things you would see in this paper is that NTP might not be suitable. But you will read it, you will find out why
Mhm.
the mathematical derivation really makes sense. Anyway, I will send it to you. You can look at it and let me know.
Yeah, I'll do. Yeah, thank
Yeah,
you, Hisham.
thank you very much.
No problem. I don't know. Any other questions from anyone? I don't see any more on the chat. Thanks, Paul, for
Uh,
sharing that other link also.
yeah, I had another question. This one was like you had a slide about clock skew that kind of showed it. Like, could you talk more about like what that, because I think there was like a 20-minute experiment, like the clock skew was going linear, and then somehow it kind of leveled off. What part of that was your experiment setup, and what part of that was just kind of unexpected?
You're talking about this slide, right? The
Yeah,
self-recovery
yeah.
behavior.
Mhm.
Yeah. So basically, uh, at this point, when you see that, the negative spans start going down, this is where we stopped. Actually, there was a different behavior. So for a lower skew levels, like, anything over 3 milliseconds, but under 10 millisecond, we saw that as you can see here, like, you can clearly see negative spans going down. So we started seeing that behavior. And at this plateau, basically, it's when we stopped running we basically, I would say, uh, yeah, the skew was still there, but the system or the negative span started to correct or recover from itself, recover by itself. So what our interpretation from this is like at this point, because the clocks are naturally drifting, so the systems are kind of aligning to each other automatically or naturally. So at that point, the negative spans, as the systems are getting closer and closer, or the time or the clock on the systems are getting closer, that's when the negative spans are going down. And at one point, we see this eventually come all the way down, and then, it fully recovers.
So
At
do you
that
think
point,
there's some correlation, or if you ran it on like a different setup, would you expect these to diverge?
yes, it does. Because that's just to check this auto recovery, the self recovery behavior. We ran few experiments with 50 millisecond skew also. What happened was like, this plateau extended a little longer, but then eventually the rate at which it came down, the negative spans, was a little slower. So what we saw, the more the skew or the more the difference. So basically, the further the systems are apart with respect to time, the longer it will take the system to the self recover.
Hmm.
That was observation. We're still working on it, but that was just the initial, interpretation that we calculated.
Yeah, very interesting. So,
And that was intentionally, why we wanted to keep the clocks naturally, let them naturally drift, because sometimes, because if you don't have a continuous P2P traffic coming into clock to correct the clock, uh, you know, yeah, I mean, that's when you want to really see, because, if a system is getting corrected, yeah, you're blinded by that, but that's when we wanted to see what happens if the clocks are not getting corrected. But yeah, so don't have a formula or something, or correlation like something like, but so far we are, based on different skews that we injected, like how the system and how long it took the system to self recover. That probably is, because of like system trying to all these four nodes are trying to align to each other eventually. Any other questions? Anything?
By the way, Ankur, you will publish your paper in because you add lots of changes to it.
Right. Yeah. I mean, I wanted to just run few more experiments, Hesham, and yeah, I'll
That,
probably include
that,
some of the latest results, and
yes,
then we can do that.
yeah, that would be great. It would be very
Yeah.
good paper.
Yeah. Uh, yeah. We also have David on the call, who is, actively helping run these experiments in his lab. David, I don't know if you want to say some words or any comments, inputs from your side.
Oh, just looking forward to working with this. So we have a lot of high frequency trading and ton of network cards. Different. We used to be Solar Flare. They got acquired by Xilinx by AMD, but they all support PDP, and then they also have direct injection pulse per second, both in and out. And so what we're planning on having the students do is try the different synchronization methods and then run a similar sort of pipeline.
Awesome.
Well, one of the ideas I did have just while listening to this presentation, so some of these network cards, you not only can get a hardware timestamp for packets coming in, but also for anything you send, you can also get the actual hardware timestamp of when it was leaving the NIC, which can also be extremely useful because sometimes you call send at the C layer, but that doesn't actually mean the packet goes out because of various reasons, whether it's buffering or even a lock or something like TCP retransmits. It would be interesting to see though if you could then, even if you had the clocks that were messed up, potentially, could you use that along with metadata like a sequence number to then be able to figure out in real time what the relative clock offsets are within some margin of error? I mean, it's still not as good as just syncing up the NICs directly, but
Awesome. Yeah. I mean, I guess I don't have anything, that's pretty much wraps up if no more questions. Back to you, Ahmad or Hisham.
Sure, yeah, like if there's more questions, we can adjourn and we'll
Good
see
meeting, good
everyone.
meeting.
So go ahead, Hasham.
This is very good meeting actually because
Absolutely.
finally we Ankur and Professor David managed to do pragmatic work
I agree.
on this
Great,
one.
great,
Yeah,
great
Yeah.
presentation.
yeah.
Yeah.
Thank you very, very much.
Open the floodgate for academia. All right.
I
All
think I
right,
have
so
zero experience in
I will,
non-programmatic.
I will, before I send my paper to David or David is very smart professor. I don't want him to look at my paper and tell me what bullshit is this.
You are
So,
far too
so
kind, Sean.
no, not too kind. It's true. But Ankur is my friend. I love him. He's a nice guy. He's gonna be easy on me.
yeah.
Sure, I will. I will.
All
And
right.
when we are happy with it, then we can give it to David.
Yeah.
All right.
You guys are too funny.
No, it's true. It's true.
Okay. So we'll see everyone in 2 weeks then.
Thank you
Awesome.
very much, Ahmed. Have a
Thank you.
nice
Thank
day.
you.
Bye bye.
Thank you.
Thank
Bye,
you, everyone.
everyone.
Thanks.
Bye.
Thank you, Ankur.